Mr. Cubby here, and we're on page 15 of the PDF of your note packet, and we're going to be talking about, well, I'm not going to tell you what we're talking about first, because I kind of want us to figure it out. Okay, so first I just want you to do this problem. So it says your car is moving with an increasing velocity according to the following table. Okay, so there's a bunch of times, there's a bunch of velocities, but your odometer is broken, so you don't know how far you've traveled. Okay. Based on what's on this table, I would like you to estimate how far the car has traveled. Pause, take a few minutes, draw a graph, and try and see if you can estimate how far the car has traveled. Okay, so I drew a little graph here of time versus velocity. And what I'm trying to estimate the distance, how far the car has traveled on this graph. First, this is the velocity graph, and so your velocity, although they only give us those points, it's continuous, of course. Your velocity is like, you know what I mean? You're not having any holes in your velocity. It's not like you don't have a velocity at some point in time. So although they only give us these points, the graph is definitely continuous. And furthermore, it's very likely smooth, right? So you're not going to like immediately go from 10 to 20 miles an hour if you go from meters per second. If you go from 20 to 30 meters per second, it's going to happen smoothly. So this graph is not going to be, it's going to be more like, Now what exactly does it look like? We don't know. There could be little wiggles in between, like maybe it goes up and then down, but we're going to kind of think it looks something like this. So how do you take a velocity graph, though, and figure out distance from velocity? You are trying to figure out the area underneath that curve. If you didn't know that, think about a simple example. Hey, you're going 30 meters per second for 4 seconds. How far do you travel? Well, you travel 120 meters. Visually, how can you think about that? Well, 30 meters per second for 4 seconds, you're really finding the area of this region here, okay? Which is the area underneath that green velocity graph. And that gives you the distance. 4 times 3, 120. Or 4 times 30, 120. Okay? So we kind of want to find the area under this curve. We want to kind of estimate the area of this green region here. Okay. Now, the hard part about this is that's not a regular shape, right? It's not like I can just whip out one of my good old-fashioned PSGH formulas, boom. I'm going to do, it's not a trapezoid, it's not like a triangle or a rectangle. It's a weird-looking shape. So normally I'd get you guys to suggest some ways to try and approximate that area, but I'll throw out a few things that people always say. And the number one thing they always say is, why don't you chop it up, okay? And the way you could chop it up is, well, you could maybe chop it like this, and then maybe chop it like, I'm just making stuff up. The reason I'm drawing these shapes is because these are trapezoids and rectangles and triangles, and those are all shapes I actually know how to find the area of. So I could break it down into geometry shapes that I actually know how to find the area of. That'd be one strategy. Use circles, maybe? Totally. You could use other geometry shapes you know how to find the area of. And that's what we're going to do. We're going to take this problem of finding the area of this irregular region, and we're going to approximate it using an easy shape. And in fact, we're going to use the easiest shape to find the area of. What's the easiest shape to find the area of in the whole wide world? Well, it's actually a square probably, but we're going to use rectangles, okay? So we're going to draw little rectangles. And I'm going to draw a rectangle like that, and a rectangle like that, and a rectangle like that, and a rectangle like that. And this last one's going to be kind of messed up. I'm going to draw a rectangle like that. And I'm going to find the area of those rectangles. I'm going to say that's kind of close to the green region. Okay, let's do that really quick. So this one would be, they'd all be too wide. How tall would they be? Well, I'm going to use my table to help me here. This one would be 50 tall. This one would be 48 tall. This one would be 44, this one would be 38, and this one would be 30 tall. So the area of this one would be 100, 96, 88, 76, 60. I could grab my calculator and add those all together real quick. Do it in my head, but feels like a calculator kind of day. I got 420. So one estimation would be, you went, I don't know, maybe like you went 420 feet. Oh, sorry, this was feet per second, not meters per second, whatever. You went 420 feet, but I know what you're thinking. You're like, Mr. Cuddy, those box rectangles aren't the same size. They're too big. And that's true. They're definitely an over approximation. So you could definitely look at this and say the actual distance that you went, the actual area of the green region is less than 420. You know what else you could do? Draw the rectangles a little different. Actually, we'll talk about this in a second, but I'll show you real quick. So instead of drawing the rectangles like that to make them too big, I could start them over here. Draw the rectangles like this. Still drawing rectangles, still using those y values that I know, but I drew these rectangles in a different way, and we'll talk about that in a second. And the result is that these rectangles, ignore that overlap there, that's just me being these rectangles definitely under approximate the area, right? You look at that region represented by the blue, that's smaller than the green region. But I could do that same thing and I get something smaller than what the actual area is. Okay, so we're going to talk about ways to approximate area of the curve, and we're going to focus on using rectangles. I know what you're thinking. I really want to squeeze in a triangle there because it'd make it better. I'm totally with you. It'd make it more complicated. And it's actually going to be unnecessary for what we do. We're just going to use rectangles now. But if you think about using rectangles, how could we improve our estimate? Well, those rectangles are okay, but it'd be kind of cool if I could like draw more rectangles. You know what I'm saying? Like it'd be cool if I could like draw a rectangle there and then another. It's a little sloppy, but you know what I'm saying. Cool if I could draw like a rectangle there, and another rectangle there, and another rectangle there, and another rectangle there. Because more rectangles would be less error. Like that. I'll throw up a Desmos thing. Wait one sec. Okay, so let's say you were trying to like approximate the area under this curve from here to here. Here I've drawn 4 rectangles, yeah, but there's definitely like big gaps, right? Like those, I'm not very accurately estimating the area under that curve. If I increased the number of rectangles, look at the white space. The white space is the error. Look as I increase from 4 to 8 rectangles. Less white space. If I go from 8 to 20, now we're looking at very little white space, right? Very little error. If I go from 20 to 100, there's still white space. It's there. It's not completely accurate, but man, it's pretty close. Okay. So a big idea is how could we improve our estimate is that we could use more rectangles. Rectangle starts with an R, Mr. Cup, not a C. Use more rectangles, okay? Now in the situation with the table above, we didn't have enough information to use more rectangles, but imagine that we actually had the curve or had the function so that we had the ability to get more Y values so we could do more rectangles. And you know what? Let's push this idea a little further. I hope you're kind of thinking about what I'm about to say, like you're getting in your calculus mindset. Oh, so you're saying if I want to approximate area under the curve, using more rectangles makes it more accurate. Well, wait a second. More rectangles makes it more accurate. So infinitely many rectangles make it such a good approximation that it would actually just equal it. Okay, so if you could use infinitely many rectangles, whatever that means, it's a crazy idea, but hey, calculus is crazy. Infinitely many rectangles, we would get the exact area. Okay, Remember, calculus likes this idea of doing something, making something infinitely many of something or making something extremely small to increase precision. And if you make it infinitely small, or you make these rectangles infinitely skinny, or you do infinitely many of them, then it stops approximating and becomes exact. Okay. What I want to focus on now is the different ways to draw these rectangles. Okay. So I think the Desmos, again, will help clear this. Sorry for the aside, but did you know back when I learned calculus, I didn't even have Desmos. I had to do all this, no Desmos, just had to do it by hand. Okay, so here, if you look at those four rectangles the person drew, they drew them starting with the left, and that's how they decided how tall to draw the rectangles. So just saying draw four rectangles isn't enough. You need to tell the person where to start drawing them, how tall to make them. And in this case, you're using the left side to decide how tall the rectangles are. Alternatively, you could use the right side. And you'll see here, they started on the right side of the interval, and that's how they determined how tall to draw the rectangles. They still drew four rectangles. These four rectangles are the same width as these four. They're just using a different method to determine how tall to draw them. This way is called right-hand rectangles. This way is called left-hand rectangles. Okay. And obviously, they differ, right? Like here, the left hand is clearly an under approximate, and here the right hand is clearly an over approximate, but that's not always the case. Watch this. Here, these are the right hands, and the right hands are under approximating, and here are the left hands, and the left hands are over approximating. What changed? Whether the function was increasing or decreasing changed. Okay. Anyway, let's actually do some of these. Cool. So we're trying to find the area under this curve on this interval, so between this x value and this x value, and we're going to approximate it with rectangles. Again, we're not going to really mess a lot with the other shapes. We'll do a little bit with trapezoids, but mainly we're going to focus on rectangles. Let's do, so our intervals from -1, x value of -1, to an x value of 3. Just to be clear, we are trying to approximate this. Sorry, the graph is kind of shady. So we're trying to approximate this yellow area. That's the area that we're trying to approximate. And we're going to do it first with four right-sided rectangles. For rectangles, we're going to start them on the right side. You usually see here them called right-hand rectangles. Okay? Four right-sided rectangles. So when I go to draw the rectangles, I'm going to start at the right. By the way, my interval is 4 wide, and I'm drawing 4 rectangles, so each one's going to be 1 unit wide. So I'm going to go to the right, all the way to the right, and I'm going to draw 1 rectangle from there, 1 wide. There's my first rectangle. Then I'm going to go here. That's how tall my second one's going to be. Again, I'm using the right side. So then the right is going to determine how tall the third one is, and then the right is going to determine how tall the fourth one is. There are my 4 rectangles. Those are right-hand rectangles because I used the right side to decide how tall to draw the rectangles. Okay? Then I actually find the area of those rectangles. Those rectangles are all 1 wide. But I have to figure out how tall they are. That's where like a table comes into play. It's helpful. Okay, so if you look at this little table, we have 1 rectangle that's 5.5 high, 1 rectangle that's 3 high, 1 that's 1.5 high, and 1 that's 1 high. When you did right-hand rectangles, something kind of cool is if you're looking at, so this is a little confusing, but hey, from -1 to 3, although it's a distance of 4, there's actually 5 points, including both the endpoints. So, but since we did right-sided rectangles, right-hand rectangles, we actually used these 4 y values, and we didn't use the leftmost one because we had right hand. Anyway, to finish this up. So we're doing the area of these rectangles. They're all 1 width. We're going to add them all together. And then the heights are 5.5, 3, 1.5, and 1. Add them all together, 4.5, 5.5, 11. Okay, so that's one approximation. This looks to be an over approximation because there's more overlap. There's more over than there is under. Just one little part's a little under, but we're not sure. Okay. Okay. Why don't you try and go ahead and do the same thing with left-sided, 4 left-hand rectangles. Okay. So using left-hand rectangles, you should have gotten an approximation of 7. Again, because we're not using that many rectangles, these aren't very good approximations. Alternatively, they could tell you to use upper rectangles. You don't usually hear about this as much. They might call those circumscribed or max rectangles. Basically, they could tell you, hey, when you're deciding how big to draw the rectangle, just use the upper one. So in this case, I'd use the right side for the first one, because that's what will make it over approximated. For this one, I will use the right side as well. For this one, just trying to color. For this one, I will use the right side as well. For this rectangle, I'll use the left side because that would make it bigger. Now I've ensured that all of those rectangles are bigger. So it's definitely going to over approximate. And this one would be, I'd have 2 of them that were 1.5, one of them that was 3, right? Isn't that what my numbers is? Yep. And then one of them that's 5.5. And again, these are all wide, or 1 wide, because I'm using 4 of them in the interval is 4 wide. And I do math, 3, 6, 11 and a half. That would definitely be an over approximation because I used upper rectangles. You can also use lower rectangles. I don't even want to type this one out, but let's just show you what I'm talking about. When deciding how big to draw this rectangle, you'd use the lower one. These aren't very common. Mostly it's right hand or left hand, or midpoint. We'll talk about that. This rectangle I draw like this. This rectangle I draw like this. This rectangle I draw like this. Those are all the smaller rectangles. So in this case, well, I guess I'll figure out it's 1, 1, 1.5, 3. 6.5 would be the approximation using those lower rectangles. Okay. Flip the page. You can also approximate it with 2 left-hand rectangles instead of 4. Fewer rectangles is very likely to make it worse. Not always, but usually it's going to make it worse. Okay. So if I was going to use 2 rectangles and the interval is 4 wide, then each rectangle is just going to be 2 wide. If I was going to do left hand, I'd get a rectangle like that and a rectangle like that. And in this case, wow, that's a bad estimate. Okay, but it's an estimate. I'd have a rectangle that was 1.5 tall. The other one's also 1.5 tall, but they're both 2 wide now. So I'd add those together and I'd get 6 for an approximation of the area under the curve. Again, with only 2 rectangles, it's not good. The other way you can do it, besides left-hand rectangles or right-hand rectangles, is with midpoint rectangles. This one's a little trickier, so I want to slow down here. If I was going to do midpoint rectangles from -1 to 3, and I was going to do 2 of them, I'm still just doing 2 rectangles because the interval is 4 wide and I'm drawing 2 rectangles. But when I was deciding for this rectangle, how tall to draw it, instead of using the left side or the right side, I could use the middle to dictate how tall to draw it. So when I went to this one, if I was deciding how tall to draw this rectangle, I could actually use the middle to do it. And that's just a different way to draw rectangles. Sometimes midpoint rectangles will be better. Sometimes they won't. Finally, I want to say one last thing. We said more rectangles is better, right? So you'd probably want to do a lot. And you could do something like 32 right-hand rectangles for a problem like this. Just telling you right now, that would be a huge pain. Okay, so later on, probably early next week, I think, we talk about kind of a way to automate this process. Because doing this by hand works for 4 rectangles or 8 rectangles or whatever. But if you try to do 32, we need like a more systematic way to do it, and we're going to talk about that. Okay. Last thing, real quick. What we just talked about was approximating the area under the curve using rectangles. We used right-hand rectangles, we used left-hand rectangles, we used upper rectangles, we used lower rectangles, and we used midpoint rectangles. People also call what we just did doing Riemann sums. Okay, we did a Riemann sum. Okay, that technique that we just did for using rectangles to approximate area under the curve is called a Riemann sum. Why is it called a Riemann sum? This guy right here, Riemann. He looks like your classic calculus boss. Yeah, good beard, good beard. Anyway, so if someone says, hey, do a Riemann sum, they're talking about doing right-hand or left-hand rectangles to approximate area under the curve. Cool. All right, that concludes this video, guys. Thanks for watching.